Okay, so here's where we were last time. So we were talking about partial derivatives, and we mentioned the notation. So here's the notation representing partial derivatives. One of the more important things to remember about partial derivatives is they are unit directional derivatives. They are unit directional derivatives, right? So, and then of course, don't forget one of the most important things to know about unit directional derivatives. They are directional derivatives, right? So, just with, further refinements. Okay. So, let's, remind ourselves of our interpretations then, right? So, as unit directional derivatives, partial derivatives are the things that you multiply by input change magnitudes to get output changes. So again, asterisk, right? It's not like this is what you multiply by exactly the input change. I mean, the input change is in fact a vector, right? We're multiplying by a scalar, the magnitude of the input change. But again, it's got this kind of factor kind of look to it, and that is appealing. In the a rare situation where your input change actually is, if the rate of change or if the actual change of the function is actually a unit vector, right? Then it is literally the directional derivative. But that's sort of a rare circumstance. Okay. But also don't forget, as a unit directional derivative, partial derivatives are slope of tangent lines to the curves that are cross sections of the graph. There's a lot of words that go into saying this. A common sort of sloppy version of this is to say, partial derivatives are slopes of graphs. And that's kind of true, but there are a lot of little details we have to recognize. Slopes of graphs, well, it's really slopes of tangent lines. Tangent lines to a particular cross section, and of course cross sections of surfaces are curves. Right? So you can't just say the slope of the tangent line to the graph, because the graph is a surface that has lots of tangent lines. Right? You have to say exactly which tangent line are we talking about, and specifically we're looking for the cross section in the direction corresponding to the variable that you're taking the partial with respect to. So if you're taking the partial with respect to xi, then we're talking about the slope of the tangent line of the curve, that's the cross section of the graph, in the xi direction. All right. Okay, so a couple of examples that we'll do here. First of all, what is the slope of the tangent line to the cross section? Right off the bat, you see slope of the tangent line to the cross section of the graph. And right away we know that the answer is going to be a unit directional derivative. That's how you compute slopes of tangent lines to graphs. All right, now which tangent line? Cross section in which direction? Cross section in the x direction. And that means that not only are we going in the direction of a certain unit vector, we're going in the direction of a unit vector that points along an axis, parallel to an axis. So that tells you we're not just looking for a unit directional derivative, we're looking for a partial derivative. And specifically, because we're going in the x direction, partial with respect to x. Partial derivatives are easy to compute. Right? For the purposes of this calculation, x being the only variable, we have x squared times this great big constant, and then plus this great big constant. Right? So that didn't, there we go. So when we take this partial with respect to x, 2x times that constant plus, and then of course the derivative of this constant is 0. So really easy partial derivative to compute. Now, last little note, that partial derivative is a function. The answer to this question is not a function. We're looking for a specific value of this partial derivative. We're looking to evaluate this slope, this partial derivative, at the point 2, 1, right? So that's what you plug in at the end, having taken the derivative, plug in the point 2, 1, and there you go. There's your answer. It's 4. Everybody on board? Okay. All right, a little more quickly through this next example. We've got a bird flying through the air. The bird is at a certain point, moving with a certain velocity. We are asked, let's see here, how fast is a certain function changing? So we have been asked to compute a directional derivative, right? We're given an input point and input velocity. We're given an input rate of change. We've been asked to compute an output rate of change. That's exactly what the directional derivative does. Okay, so now this is one of those circumstances where the directional derivative is less convenient than the unit directional derivative. The unit vector representing the direction that this velocity is in, that unit vector is very convenient. 0, 1, 0. That 5, I might as well just factor it out rather than sort of dealing with it all the way through the calculation of this unit directional derivative. So let's do that. So let's take advantage of the fact that it's unit directional derivative. Then we further capitalize on the fact that not only is this unit vector relatively easy to deal with, but it is a standard basis vector, and therefore I can rewrite the unit directional derivative as a partial derivative. And at that point, again, it's all over, but the details, you just have to take a derivative with respect to y of that expression. Don't forget to use the chain rule. A lot of students forget to use the chain rule in a problem like this. By the way, notice you kind of have to use the chain rule twice, because this is a composition of 3 functions. We start off with x plus 2y plus 3z. Then we take the sine of that. That's already a composition. And then we take the square of that sine of that inside function. So there's 2 different chain rules in there. I'm going to let y'all read through the details. Again, calculus is single variable calculus is a prerequisite for this course, so make sure you're good at this kind of thing. Okay. So y'all may recall from Calc 1 class that in the same way that you can take a derivative of a function, you can also take a derivative of a derivative. After all, if you have a function, when you take the derivative, the result is another function. Take as many derivatives as you want. So likewise here, right? Notice that if you look at, for example, you look at this function, there you go. There's a function of 2 variables, and when you take the partial derivatives with respect to x, and then later take the partial with respect to y, these are also functions of x and y. So you can ask, what are their partials? So, for example, partial of f with respect to x, you could take its x partial. You could take its y partial. And likewise, partial of f with respect to y, you could take its x partial. You could take its y partial. So these are called second partials. A notational sort of convenience. Let's look at this one here, for example. And this is just notation. This used to bug me, by the way, when I first saw this. You're taking the y partial of the x partial of f, and then you just kind of look at the symbols that are written down in there, and notice that in the numerator, I air quote where I say numerator, because this isn't really a fraction exactly. It's a limit. It's a limit of a fraction, sure, but importantly, it's not itself actually a fraction. Right? There is no thing that we've defined that is partial f. It's not a thing. Fractions are ratios of things. That's not a thing. So this is not a fraction. Okay. Anyway, let's just notationally, for notational purposes, let's just kind of ignore. Let's pretend that this is actually a fraction. But anyway, so pretending, we have partial and then another partial, and so what people will write, however nonsensical this kind of is, people will write partial squared. It's not. There's nothing being squared. So make sure this is just sort of written for notational purposes. Anyway, so you'll see second partials written like this all the time. Get used to it, yeah.
When second partials are written like that, does it matter what order you do?
That is a great question. I'm going to say for the moment, temporarily, the answer I'm going to give is yes, and let's put, whichever partial derivative you're taking first is kind of going to be on the right, you know what I mean? And the one that you do next will kind of be on the left. And let's make sure to put them in that same order here. And I'm going to put a great big asterisk on the answer that I've given. I've said that it does matter. And it only does matter for the moment because we don't confidently know whether it does or doesn't, and we'll address that in a few minutes. Okay. All right. So, all right, what do these things actually look like? Let's talk about a second partial with respect to y. Let me switch colors because green is friendlier. Second partial with respect to y. What does that look like on the graph? I asked rhetorically. Well, in this process of computing the second partial with respect to y, keep in mind, the very first step in this process is I'm going to take the y partial, and the very first step in that process of taking a y partial is to say x is fixed. All right, so we're going to fix x. X is now constant for the purposes of that first partial with respect to y. And when I fix x, I'm effectively taking a cross section. I'm looking at that little bit of curve right there. It's a cross section perpendicular to the x-axis. You might say it's a cross section in the direction of the y-axis. Don't get those confused. All right, it's easy to inadvertently think, oh, well, it's a y partial, so I want to take a cross section perpendicular to the y-axis, and that's not how it works. You want the cross section in the direction of the y-axis, which means perpendicular to the x-axis. You got to look at the picture, think it through, acknowledge this sort of potential for confusion, and try to make sure to get that straight. Okay, so that was our first step. Make x constant, and then we take the derivative of the resulting single variable function of y. And then, by the way, the very next thing we do is we then take a y partial, which says further continue to consider x constant. So here's a different way to say this whole thing. For the process of taking this second partial, throughout this whole process, I'm treating x as a constant. So let's say it like this then. This second partial says I'm going to treat x as a constant. Therefore, I'm looking at this cross-section. And while in this cross-section, I'm going to take a second derivative. I'm going to view this as this little purple curve here. I'm going to view that as a function of a single variable y. And I'm going to take its second derivative with respect to y, of course, because that's the single variable. And here's the good news there. We already know a geometric interpretation of a second derivative of a single variable function. It's concavity, right? So what I have here, this little curve as I've drawn it concave up, that is the geometric manifestation of this second partial being positive. Just like it was in Calc 1. Okay. All right, so the second partial with respect to y, positive means that cross-section's concave up. Negative means that cross-section's concave down. So no surprises there. It's exactly what you would think. By the way, you can think through for yourself if you were taking the partial with respect to x. You'd be looking at a cross-section kind of like that. The cross-section would look something like that. And that's morally same idea. If the second partial with respect to x is positive, as it is here, it's that cross-section's concave up, as it is here. Okay. All right. Now, here, I'll say that this is... Oh, yeah, you have a question.
Is that cross-section, where do you get, like, 2 on either side?
Well, we're taking the cross-section through this point, right? And we're taking the cross-section for the purposes of that partial. We're taking the cross-section perpendicular to the x-axis through that point. And so there's really only one cross-section, and it's like that.
Maybe I'm just misunderstanding this, but wouldn't there be one on the negative part of the y-axis?
Yeah, sure. Well, this cross-section is actually a whole curve like that. Right? But keep in mind, I'm trying to make an interpretation of what does this cross-section look like at that point. You know, what is the meaning of the partial derivative at that point? And at that point, we're just looking at just there on the cross-section curve. Yeah, totally. Does that make sense? Yeah. Cool. Okay. Let me summarize this by saying, if you're taking second partials with respect to the same variable twice in a row, like y partial of y partial, second partials mean geometrically exactly what you would think they would mean. That's good news. Okay. All right. Now, here's what is not analogous to a single variable. What if you were taking a y partial of an x partial? So first partial with respect to x, subsequently partial with respect to y. If I were to ask the rhetorical question, what would we expect based on our single variable experience? What would I expect this to be? The answer to that rhetorical question has to be, there is no analog in single variable. There's only one variable. You can't take derivatives with respect to two different inputs if there aren't two different inputs, right? So this is uncharted territory. There is no expected, we have no idea how this is going to turn out. Okay. So here's my picture of how to think about this. So reminder, we were looking at the partial with respect to y of the partial of f with respect to x. This is what we want to try to come up with some geometric interpretation of. And so we'll start off looking at partial with respect to x. On this picture, what does a partial with respect to x look like? Well, at, let's say, that point, a partial with respect to x says I'm going to look at a cross section in the x direction. I'm going to look at the slope of the tangent line in that direction. This is the value of partial f with respect to x at that point. It means this slope in this direction. Okay. So let's then ask the question, well, what is this y partial thing? How am I going to interpret the y partial here? We're going to take a different point of view on partial derivatives here. I'm not going to interpret the y partial as a slope. It's not helpful here. Part of the reason is y partial, if I say, what does the y partial look like? I could only interpret that as a slope if I were looking at a graph of the thing I'm taking the y partial of. And that's not what I have. I don't have here a graph of partial of f with respect to x. I have a graph of f. Right? So I can't make any sense out of this y partial from a graph point of view. I'm not looking at a graph of this thing. So, different point of view I want to take. Remember, a partial derivative is a directional derivative. So, a different point of view that we have on directional derivatives is, suppose you start moving in the direction indicated by the input vector. Right? Partial with respect to y means we're moving in the y direction. Directional derivatives mean how fast is this thing changing as you move in that direction? So it's not about slopes in the y direction. We're not looking at a graph of this blue thing. But I can reasonably ask, okay, I've got this partial derivative with respect to x. I interpret that x partial as, well, slopes in the x direction. And I could imagine, the picture is going to get muddled pretty fast here, but I could imagine various cross sections that I'm taking in the x direction. now that we've seen clearly that we're taking cross sections in the x direction, let me try to recover a little bit of sanity in my picture by deleting those planes. For each one of these points down here, I've got a sort of a representation of what the tangent line in the x direction would look like. The y partial of the x partial is saying, as I move in the y direction, how are those x direction slopes changing as I move that way? And what I have drawn here, this example that I have drawn, note I didn't actually even draw the graph of f. It would just make the picture too muddled. But this is an example of the x partials being positive and then decreasing and eventually, in fact, being even negative. So what we have here is a picture of this mixed second partial. Oh man, hang on. Being negative. This is what it would look like, for example, with this mixed second partial being negative. So how do you want to say that? Is it concave something? And it's just not. Right? This is not about concavity. You might say this is kind of representing a way in which the surface is kind of twisting. It's like you have a flat piece of surface, like rubber or whatever. It's like you're twisting it one way on one end and the other way on the other end, and you can imagine that puts kind of a twist in the surface. That's what the mixed second partial is measuring, is a sort of a twist that creates, by the way, you'll notice kind of a sort of a Pringle-y kind of shape, in the sense that it's kind of, you can see it's kind of down all over there and it's kind of down over here, but it's kind of up over here and kind of up. It's like there's an upness in that angled direction and then sort of a downness in that direction. It's a weird sort of thing, yeah.
You kind of think about it like how the normal vectors changing like along the surface, like to each curve or whatever.
Yeah, sure. There'd be a point of view there. Yeah. As of the moment, we don't know how to understand that normal vector, but yeah, you could certainly take a point of view there. Yeah. Okay, it's a hard thing to get your hands on. Again, if you're grasping for, okay, so this is like in single variable, this is analogous to. There isn't. Right? There is no single variable analog to this. So don't try. Okay. Oh yeah. Mm-hmm.
So just one more time, look at the picture.
Yeah.
Those individual lines, are they going only along that line, or are they going perpendicular to that line?
Each one of these blue lines that I have is parallel to a plane that's in the x direction, a vertical plane in the x direction.
So they're going perpendicular to the green line.
They are all going perpendicular to the green line. That's right. They're all in planes that are literally perpendicular to the green line. That's right. Okay. All right. Very last thing in this section, then we'll call it a day. Somebody asked very quickly when we started talking about second partials, does it matter which way you go? And for sufficiently nice functions, it actually doesn't matter. Right? Now, there are conditions. The function cannot be arbitrary. The function has to have a nice regularity to it. Namely, those second partials all have to be continuous. There are some weird anomalous counterexamples that one can construct if one is inclined, if one is, the kind of person who likes to construct weird anomalous counterexamples. Right? You can make counterexamples that do not satisfy this constraint here, in which these would then, so if those partials are not continuous, then those mixed second partials do not have to equal to each other. But if this regularity condition is satisfied, and hey, good news, right? Most of the time, everything in sight's continuous. Most of the time, in real life, right? Not always, but very often anyway, everything in sight's continuous. In which case, doesn't matter which order you go, doing the xj partial first followed by the xi partial is the same as doing the xi partial first followed by the xj partial, and therefore it doesn't matter which order you write them down. Okay, is everybody good? Alrighty, that's a good stopping point. We'll call that a day, and see y'all tomorrow.